All right, welcome back. We are GAME3001, that's Game AI at George Brown College in the summer 2020 semester, and this says week 14, but actually it's week 12, and this lecture is typically reserved for the last week of class, or the second last week of class actually, but I've kind of included it today because of our compressed schedule during the summer. So we're going to be talking about machine learning and in games specifically, and reinforcement learning in general. How do we make AI learn? That's what this lecture is all about. But before we get to that, I want to talk about next week a little bit. So next week on Friday, there will be no lecture officially. What I'm going to do is I'm going to hold office hours during our lecture time. So between 10 and noon, we'll have office hours, so you can come online, schedule time with me. It can be ad hoc, I don't mind, but I'll definitely just be available for you next week completely for anything you want. And that means things like assignment help, because your final assignment is due next week on Friday at midnight. So anything like that. So from 10 to 12, I'll be doing just regular office hours, marking help, anything like that that you want, for me to assist you with for this course. And then during the lab periods, that's between 12 and 2 and 3 and 5, I will also be available for technical help with your assignments or any other thing that you want. So I'll still be available physically with you. It's almost like an open session next Friday. Attendance will not be mandatory, so you don't have to attend if you're good. I will not be making any additional announcements or anything like that. I will have one Zoom session code, so there will be only one for the whole day, and I'll pretty much will be keeping the Zoom session open throughout the day, where I'll be popping in and out as required. Okay, so that's what's going to happen next week. You're not going to get multiple Zoom codes or whatever. There'll be one for the entire day. And then for your final test, which is basically next week, what I'll be doing is I'll be releasing it on either Monday or Tuesday. It'll be true, false, multiple choice type format. And what you'll be doing is you'll have the entire week pretty much from around Monday or Tuesday to whenever it gets released to Friday at midnight to get it done. And again, it'll be the same kind of format that we had, let's say, for your midterm test. Alex did the midterm test, right? So it'll be kind of like that, where you'll be answering true, false, multiple choice kind of questions. But I'll give you multiple attempts, so you'll have a couple of attempts to do your test, and it'll be the best attempt out of 2 that you'll get in order for you to get your highest mark possible. So that is the plan for next week from a final test perspective, okay, and from a lecture thing. So there's not official lecture, just to repeat, no official lecture next week. I'll also make an announcement later on, which is basically going to say the same thing. You'll only have until Friday to do your final test. If you don't get it done by Friday, there's no extensions, all right, unless there's an extraneous circumstance, that kind of thing. But you'll have pretty much all week to do it, so there's no specific time frame that you have to do it. You can also do it if you're booked, or if you're very, very busy throughout the week. You can also reserve our lecture time to get it done. And again, I'll be here during the last day to assist you if you need to have a reset done or something went wrong. But basically, the 2 attempts that you'll have for your midterm or your final test is that way. If there's any technical issues, you have an additional attempt or so to get it done. If you have special requirements, as an example, so let's suppose you have a requirement to get your you need more time or something like that, please again just let me know. I know there's some people that also need to have the test released early, and what I'm going to be doing is again, you'll have all week to do it next week for the most part, and then you can do it throughout the week. You don't have to wait till Friday to get it done. Okay. So, any questions around the test? I know some people are just coming in. We're just talking about the final test and the final lecture and labs. Any questions around the test or the lecture lab for next Friday? As next Friday is the last session with us. Maxim says no. That's good. Thank you, Maxim, for that. Anyone else have any questions or concerns? Pauline's good too. Thank you. Yeah, so again, thank you for that. If you do have a question or if there is a concern that comes up between now and next Friday, please let me know. I want to try and be as accommodating as possible in these crazy times. Absolutely, Paul. You can always email me. Okay? All right. Let's get moving on this one. All right, so we've been talking a lot about behavior in this second half of semester, and that's really what this whole part has been about. And actually, that's what your assignment 3 and assignment 4 have been about: behavior. The first half, like we said before, just to recap, was all around steering behaviors and pathfinding, which is kind of like I would say, a fundamental technique for any kind of AI or autonomous characters. All right, that's what those things are. Here with learning, this is kind of something that we want to talk about, as we're moving closer to advancing the art of artificial intelligence for games going forward. So, machine learning is pretty hot these days, and we hear about it all the time. Right? Machine learning. What is that? It is an aspect, I would say, of artificial intelligence. Artificial intelligence is pretty big. It's almost like the set of all different things that you can do, with the computer, in terms of how it, you can make the computer think or act like it's more alive or human. But machine learning is kind of a subset, I would say, of artificial intelligence. And when I think about machine learning, I always think about statistics on steroids. That's what I kind of think about. If you're someone who loves stats and probability, machine learning is for you. Okay. How does it work with games? Well, it's the learning aspect of what machine learning is about that we want to tap into for games. So imagine you want an AI that can adapt to a player, learning who you are and providing challenges. Not too much challenge, because remember, we want to kind of balance a challenge when it comes to AI. We don't want it so it's too challenging, and we don't want it to be too easy. Okay, because if it's too easy, then it's not fun. If it's too challenging, and if you're not someone who loves Dark Souls and to be killed all the time, then it can be tough as well. Although Dark Souls, there's a lot of patterns, and that's not really machine learning. So again, what the great thing is, it has the ability or the potential to make more believable kind of AI, and basically what it does is, if we want to make to provide tactical options for AI, then machine learning is the way to go. So one thing is that machine learning is not really, in general, or learning, let's just call it learning for now, is not really being used in games today. All right, and why? Because it requires another level of programming and testing. It's challenging to reproduce the results. And what I mean by that is, if we make something that is a learning machine, how can we test it? That testing is always going to be a challenge, right? So there's been some impressive things in our field, but a lot of times the challenge here is that how do we make it realistic, and how do we make it so that it makes sense for the games that we're putting together, right? So again, there's a whole bunch of different kinds of learning techniques. we sometimes call them, sometimes it's like some kind of simple matrix that we want to use, which we're going to be talking about today, called a Q matrix, and more complex, kind of learning technologies, such as using neural networks. A lot of times we've been hearing about something called deep learning. Okay, so there's different machine learning and deep learning, and deep learning is kind of a form of neural networks. And there's lots of other kinds of approaches in terms of learning and how they work, how learning works for machines. And when we classify different learning techniques, we want to kind of think about two aspects. One is when the learning occurs, like it says here, and then what is being learned, and what are the effects of the learning on the autonomous character's behavior. So what does this mean? It means like, okay, so let's say, so when is the character learning? Is the character learning when they sense you with, let's say, some kind of line of sight or whatever? What am I learning? Am I learning your patterns? And is the character learning that you're always going to the left when you enter the level? Is it learning that you always attack high and then attack low, so it can defend you against you? So that's the what part. And also, how does it affect the character? Is it going to be deterministic or more non-deterministic? So is it going to take that information and then improve to some level, or is it going to be like super hard to kill? Like what kind of learning? Why are you implementing the learning algorithm in the first place? So again, there's two types of learning that we're going to be talking about. One is called online learning, and the other one is offline learning. Okay, so think about offline learning as I run a bunch of simulations, and then I let my autonomous character, run around in my world, learn about the world, and then take that in, store it somewhere, and then do something about it when the game is going online. So online learning is something that's happening in real time. So during the game, so live while the player is playing, and it allows the autonomous character to adapt in real time, right? And the more the player plays, the computer can more anticipate what the live player is going to do. And what this does is it creates an ongoing challenge. However, all right, this kind of learning is very challenging, and the reason for it is because it's not easy from a predictability and testing perspective. Like we said, why? It's hard for me to replicate bugs that come up because it's so non-deterministic, right? It's in real time. So I'm kind of learning something in real time, and the game is picking up kind of your personal traits. Let's say if you're the player, right, and storing them somehow and adapting to you, right? So how do I know that it's acting in the right way? It's hard to troubleshoot. It's really, really hard to troubleshoot. So that's why online learning is not as popular an option as offline learning. Okay, so the majority of game AI learning technologies is usually done offline, like I said earlier, right? And the way it's done is we allow the autonomous character to learn about the world and the state of the world and different positions of the world. And this can happen for both board game AI. So things like, imagine if we're playing Monopoly, we let the player, kind of explore the game world and try and play against other autonomous characters, as an example. And we do thousands of these iterations, and we'll talk about this. And so it can get experience. Let's talk about this idea of experience, playing the game before the real, kind of a real life player comes on board, right? So they have their own tactics, okay, and strategy. So again, what happens is we have this idea of the autonomous character exploring the world, and then we store this information in some kind of database or file, as an example, And then what happens is when the player kind of acts or responds to the autonomous character, the AI, then what ends up happening is the AI has been trained to respond to their actions. That's what ends up happening over and over again. So it's kind of like an offline learning technique. So online, offline. Okay, we're also going to talk about intra-behavior and extra-behavior. We're going to talk about this. So again, simplest kind of learning is changing a small area of the character's behavior. So in other words, we don't change the whole quality of the character's behavior, but only a little bit. And really, intra-behavior learning techniques are easy to control because they're super easy to test. And this can include things like learning how to target correctly when projectiles are modeled by accurate physics. This is a great idea. So my physics are working properly. I can target because I know where the projectile is going to land. As an example, so I can estimate, the autonomous character can estimate where it's gonna hit. As an example, learning the best patrol routes around a level. Okay, so again, pretty straightforward, right? We let the character run around the level, and then we know the best patrol routes and places that, for example, characters or players might hide, where cover points are in the room. And we kind of are doing that with, in some ways, again, remember there's internal knowledge that we talked about last week and external knowledge. Internal knowledge would be like something like the machine is telling you which nodes in the game have cover, as an example, in our assignment 4. But think about, instead of having internal knowledge, the character, when we use learning, has no internal knowledge whatsoever. Okay, if it hasn't heard you or if it can't see you, the only way that it can learn to be more realistic, and that's why we use learning at all, is to explore the world and then create its experience matrix, Q matrix, or something like that, and then from there, store that information so that it can behave better when it comes to playing against the real life player. Okay, that's really intra behavior. Okay, and again, another one is learning how to chase an evading character successfully. So what you would have is a test where you would create an evading AI. And then you have your main AI learn how to chase inside a particular level or inside the game world. Okay. This is not, or something even easier than this. I'm not sure if you guys have played things like Skyrim, or I'm thinking about Skyrim again from a Skyrim AI, which is pretty simplistic, or even Oblivion earlier than that. Let's say several years ago. I would say more than 8 years ago now. If you ever fight any of the characters there, and if they're casting a magic at you or something like that, and you just happen to move to the left, as an example, it'll try and anticipate, or not anticipate, it knows the direction of your movement, and so what it'll do is, if you try and evade, it'll throw its spells, or it'll try and cast its arrows, as whatever it is, its projectile weapons, in the direction that you're moving, right? Of course, you can fool the AI by doing a slight move to the left while it's firing, and then you can, that's how it works. So that's not what we're talking about here. We're talking about not just how to fire or move around, but actually how to respond to the character. So now this can be done in thousands of iterations. This is the great thing. When you do it offline, right, you can run thousands of simulations, or tries, if you will, and the AI can be quite good, get quite good at doing those kinds of techniques, these kinds of evasion techniques, or this kind of thing. So again, this is kind of what we're talking about here, is the frontier of learning AI. So it's still quite new, even though it's been around for a while, right? And learning of behavior is really qualitatively different than just responding, or having a behavior matrix, a behavior tree or some kind of decision tree. It's not like that. It's literally, think about the autonomous character as a baby, and it doesn't know anything about anything. It's going to learn things by actually going and exploring the world. Okay. So here's an example. Autonomous character learns the best way to kill an enemy is to lay an ambush. So that is kind of part of the learning behavior, right? or an autonomous character that learns to tie a rope across a back street to stop an escaping motorbiker. All right, that would be awesome. Again, this is kind of at the leading edge. This is not what we're talking about. Inter-behavior. So again, there's inter-behavior and intra-behavior. So intra-behavior is the one we talked about before. Inter-behavior is the kind of the almost like external knowledge, or if you will, the ability for them to learn, learning from scratch. Think about this as unsupervised learning. And we're going to talk about the difference between supervised and unsupervised learning in a second. Okay, so unfortunately, this kind of AI is limit of what we can do. It's not always possible that characters can just learn from scratch and become better and better. One of the things that I've always thought about is whenever you play a role-playing game, maybe we've talked about this before, right? You play a role-playing game and you start playing, and you're in your mind, you're thinking, I'm just going to play the game and not do the main quests, and do all the side quests or whatever, get more powerful, then go back to the main quests. People do this, and it's okay. And sometimes the game will respond. At the higher level you go, it'll throw higher level enemies at you, so actually it's worse if you don't hit the main quest early. Or sometimes it'll just rebalance the entire game based on your level. So it's challenging but not impossible. But wouldn't it be nice if you didn't go on the main quest when you started the story, that the quest went without you? That would be nice, almost like a time limit in some ways. Or the world kind of, depending on what you did, your actions would have a ripple effect on the game world. Almost like, the way the story would evolve would not be deterministic. It would not be a deterministic story. There could be many different outcomes, many different story endings, if you will, for your particular quest. And I'm not talking about No Man's Sky thing. I'm talking about like with procedurally generated worlds necessarily, but almost like a procedurally generated story, or a story that happens because each of the AIs that are inside the game world are learning and understanding what's happening around them. They even learn from other AIs. And so you set almost like this genetic algorithm in motion, and then, again, we're dreaming here, and then somehow the AI morphs and changes the game world and the story, of course, with some tweaks and some, I would say, rules that the game is going to enforce, so that there is some kind of direction for the story, so it does resolve somehow within a certain time frame. And it's not going to be something that's going to resolve in an hour by luck. It's going to be something that's going to last a while, so you get your money's worth out of the game, but challenging enough so that every single time you do a run through, it's different and challenging and interesting. That would be the dream. But again, that would be something like where we use inter-behavior learning for all the AIs in the world. Nice idea. Right now, science fiction. Okay. All right. So there's also something else called overlearning, and a lot of times it's easy for us to create something like an overfitting or overlearning curve. And the reason for this is, let's say, for example, we expose the AI to a number of experiences, and it learns from them, and it only learns the response to those situations. So example, think about this as overfitting in some ways, right? So it runs around with other AIs like itself, and an AI that kind of simulates what the player is doing. And so, but the player is also an AI, right? So what ends up happening is the AI that is created is learning, quote unquote, by exploring the world, is learning from itself. And so what ends up happening is it creates almost like a matrix of behavior that is actually wrong, right? And what's happening is as things continue, it's going to continue going down that path of kind of making the wrong responses and being actually deterministic in some ways, as opposed to what we want the other way, right? Another example is the AI is being trained by testers, game testers, and depending on the level of the game tester or QA tester, if they're great players, then the AI is going to learn how to defeat an awesome player, as an example. But if they're poor players, then the AI is going to learn to defeat kind of not such a great player. And in the beginning, when you start learning a game, depending on the experience you have in general of playing, like people have a great experience of picking up games. I don't know if you know anybody like this. Brand new game comes out, and someone that might jump on the game and they can complete it within half the time that someone else can do it, because they're so good at common controls, moving around with a gamepad or mouse keyboard combination. Their reflexes are really good, and they've trained their reflexes. I'm talking about a human being here who's trained their reflexes or knowledge of how to play games over their life, whatever it is, right? So imagine someone like that play testing with an AI. Well, the AI is going to be really good playing against that player, as an example. And if that player consistently does the same things, and if we always train the AI to respond to that particular player, as an example, then we can have this idea of overfitting, which is I'm going to gear the AI towards one particular style of play as opposed to other types of play. Maxim, do you have a comment, or did you come on by accident? I'm guessing it's by accident. Okay, there we go. All right, so that is the idea of overlearning, okay? So that's also a bad, or it could be a pitfall for us, right? So what we want is really the idea of this technique is the idea of decision, how to make proper decisions, right? And decision learning is another aspect. We wanted to learn how to make the proper decisions based on the game state, okay, the state of the world. That is where we want it to be, all right? It's not just about using steering behaviors, but also some strategies in the game. Okay, that's what we want, from an AI perspective. If we can think about learning in general, that's the direction that we want. So in this case, we have some kind of observable values, things that the autonomous character can detect and record. All right, that's what we want to be able to do. And this could be things like the distance to the nearest enemy, the amount of ammo left, all this kind of stuff we talked about last week. And then we need to associate, right, the decisions in the form of single behavior option to choose from with the observations. And this is the idea of what we talked about last time, which was we have observations, and we might have this idea of a goal-oriented behavior like we talked about last week. And over time, the AI can learn which decisions fit with which observations and then can improve its performance. That is something that we can do, right? So we want to improve its performance over time, right, to the point where it's better at making the right decisions. Example, we talked about this earlier with inter behavior. Where is the best place to hide? As an example, what is the correct path to leave the game world? If I'm going to leave, what's the shortest path? I can learn about these things, not because I'm using a pathfinding algorithm, but because I'm recording, different kinds of steps and different options by allowing the AI to explore the world. So there's different kinds of supervision that we can do. Sometimes we use supervision to help the AI improve performance. And a lot of times, there's two types we talk about. We talk about weak supervision or strong supervision. Okay, those are two types of algorithms we can use. Okay, so I want to talk about those two things. So think about strong supervision. This is where we have a set of correct answers that we give the AI. So correct behavior. We've already planned out what the behavior of the AI it should be to make it correct, to win, let's say. Almost like winning strategies that we bake into the game. And then we have a series of observations, again, associated with the behavior that should be chosen. So almost like, hey, this is really good behavior, do this, almost like rewards. We want to reward the AI for doing good things, and we want to punish the AI for doing bad things. Strong supervision, right? As an example. And the AI keeps track of these observations and decisions, and sometimes it watches the human player, as an example. Sometimes we bake it into an algorithm or a matrix, and then it can learn to act in the same way as a player. So example, let's say I want the AI to be to observe someone like a really good player, like we talked about earlier, someone who's a person who's played games for a very long time. Okay, so we want an AI to observe them and then mimic what they do, right? So think about, hey, that's really good, and almost like the AI designer would kind of coach strong supervision. As an example, think about this as really truly supervised learning, where you're looking at the AI and going, okay, that was really good. Let's add this action that they've done to the really good actions matrix, and this is a bad action. Let's punish the AI when it does this stuff. And we can do this with values. We can say like, this is a positive value, this is a negative value, right? In terms of actions. So the AI can learn different kinds of, to track different kinds of players. So let's say, for example, I want to make an AI that is like a newbie. So we get a newbie player, a person who's never done it before, to play the game, a noob, right? And they play the game, they don't know what to do. We can have the AI act like that player, or a series of noobs that do the same thing, almost like a low-level AI character. You can also have an AI have a kind of a medium, intermediate, or advanced type of play simply by watching actual players play the game. All right, and then you can use that behavior to play against the player, right? So the player can, a good example of that is an FPS kind of game where you're playing PvE, player versus the environment, and the AI that's been designed in the environment have played against each other by watching other players as well. All right, so this is the way that they can be designed. Weak supervision, on the other hand, is almost like, and sometimes I think about unsupervised learning in some ways. So supervised versus unsupervised. This is like less supervision. So imagine we don't get any kind of correct answers at all. We say, we just provide, negative or positive feedback. That's all it does. But it creates almost its own matrix by exploring the world. So this is something where, when we go towards weak supervision, it's almost like learning from scratch. Okay, so that's the other extreme. So strong supervision, one extreme, weak supervision, the other extreme. Example, if the AI gets shot, then the performance monitor will provide negative feedback, you got shot. So there is some supervision, some feedback that this is a bad action, right? But more or less, the AI is on its own. It just gets some positive and negative cues in terms of what it's going to do. Not so strongly as directly watching another player, but actually exploring the world just like a regular player would do. And then it learns from it over time. So again, I would say positives and negatives of these two approaches. Strong supervision, easier to implement and get right, but it's less flexible, more deterministic. And you need somebody to teach the algorithm what's right and wrong. Weak supervision, it can learn right and wrong for itself, but is much more difficult to get right because this algorithm as a good example, could totally go and do the wrong thing depending on what kind of experiences the AI is going to have, right? So we need a balance between these two approaches. Okay, we need a balance. There's some other common AI learning techniques that I want to talk about really briefly in 2 seconds. One of them is naive Bayes classification, and this is really used for classifying kind of situations. So again, you can sit there and say it's like neural networks in terms of its classification, but it's really naive. In other words, think about naive Bayes, that's why it's called naive, has no idea about the world, like baby eyes, and then it's trying to classify situations based on the things that it observes. So naive Bayes classification, and we use this in machine learning today. Neural networks, it's more used for prediction. So I want to predict what the next action is going to be, as an example. And we can use neural networks. Neural networks have a set of different layers. They use something called a neuron. They built their algorithms around the human brain, almost like the idea that we can receive information and we can respond to information, neural networks. We have different layers. We have the outer layer and several inner layers that are hidden. And what ends up happening is with neural networks, it produces, the results can be weighted, if you will, and to get almost like a prediction classifier at the other end. Okay, so this is kind of what we do. These two options here are for machine learning, more or less. Where we want to go with games is this, which is reinforcement learning, that's what we've been talking about. So learning based on experience, which allows complex behavior encoding, and this behavior encoding is going to happen in some kind of matrix. Okay, so this is what we're going to be talking about more after this. So we've talked about supervised and unsupervised learning, and it's all usually within this reinforcement learning technique. So what is reinforcement learning? It's the name given to a bunch of techniques for learning based on experience. Okay, and the general form reinforcement learning algorithm has three components. It's got some kind of exploration strategy for trying out different actions in the game. There is something called a reinforcement function that gives feedback on how good each action is. And then there's the learning rule that links the other two things together. Okay? Each element has several different implementations, and we can optimize it depending on the different applications. So reinforcement learning is, to me, what we can use with games, right? And let's talk about each aspect: exploration strategy, reinforcement function, and the learning rule. So think about this. We would like a game character, here's the problem, to select better actions over time. What makes a good action may be difficult to think about what that is, depending on the AI designer. And it may depend on how the player acts, or it may depend on the structure of random maps that we can't design for, right? For example, No Man's Sky, again, right? So it's not like a level design thing where we let the character run around in the same level all the time, but rather it's different levels, right? It's random levels, and we want different kinds of autonomous enemies or characters to kind of have some kind of decision that they're going to make based on the game world, right? We want to be able to give an autonomous character free choice of any action in any circumstance. This is like pie in the sky thinking, and for it to work with actions that are best for any given situation. That would be awesome, right? That is the problem. So let's talk about the approach. Unfortunately, one of the things we have a problem is the quality of an action isn't normally clear at the time the action is made. So we don't know if it's good or bad, right? If we're thinking about true reinforcement learning and this is reinforcement learning to me is more unsupervised as opposed to supervised. Okay, so it's like closer to the weak supervision part. Okay, so it's easy to write an algorithm that gives good feedback when the character collects things like a power-up or kills an enemy. That's easy. But the again, the killing action may have been only 1 out of 100 actions that led to that result. So how do we get to that result? How do we get to the kill? Is it being placed in a series of actions to get there? So example would be, let's say I'm playing something like an FPS, like something like Apex Legends, which is a fairly recent game, and we get an AI to play in Apex Legends. So it's not a live character; it's a group of AI characters, or again, player versus the environment, and it's coming at you, right? And it does all these kills. How does it do the kill? Is it because it tracked the player and it hid behind cover, and then when the player came out, it selected the right weapon to attack the player based on their defenses that they had, or their special abilities? Is that how it defeated the player? That's what this means between 1 and 100 out of 100 actions. What was the series of actions? Think about the cone of possibilities when it's in a particular state that got it to make that kill. That is difficult to understand. What is the right sequence of actions, in order for it to learn, so it can do those actions again and again, and also adapt to the environment based on, let's say, random levels, right? So therefore, we'd like to be able to give really patchy information, and then give feedback when only something really good happens. The autonomous character should learn all the actions kind of leading up to the event, and good things to do, as well as so that we can track the sequence of events that led up to that particular positive action. Okay, so that is what we want. Okay. Again, think about think about the cone of possibilities in real life, right? As an example, you made a kill. How did you make the kill in the game? As an example, if you're a first person FPS player, right, kind of thing. How do you do that? Well, you gain some good skills in terms of reaction time. A lot of times it's reaction time, picking the right weapons, switching ammo at the right time, making sure that you heal yourself if you can, if you have that option, by getting some kind of stim pack or I don't know, healing potion or something like that at the right time, before, when your health gets low enough, running away when it's time to run away, and dodging or evading, in a specific pattern, and then as soon as you have the right advantage, coming back into the game. Or maybe it's around hiding, and you're a sniper type player where you're going to find the right purchase, someplace where you can't be seen and no one has detected you, and you're going to sniper a bunch of your enemies away, right? So how do you get? That's a sequence of actions that has to be gone through before you get to that particular win. So reinforcement learning, it kind of models an environment, the entire environment, as a network of states. All right, so think about this as you have a bunch of states. Let's say states SI would be the we're going to classify them as S, right? And each state has an associated reward, right? So you have a state of the game. So let's say, for example, when you first start the game, you're in this beginning state, right, where and I'm thinking about a board game right now. Let's say, again, I'm thinking about something like chess, right? Where the initial state of the game, right? Who has advantage in the initial state of the game? State initial, and this is what SI is, the initial state, as an example, has some kind of reward. There's no reward for the first, the initial state of the game. And let's say, for example, in chess, every time a player makes a move, and I'm looking at chess because chess is a kind of a known quantity in some ways, right? If player A makes a move, the whole game world has been changed. Why? Let's suppose the player moves their pawn up one space, let's say in front of their king, right? If you know chess, now the state has changed, right? The game world has changed, where there's one square that's closer to the middle of the board, which in chess is one of the winning strategies, control the middle of the game, the middle of the board. It's one step closer to the middle board. The state of the game has changed, and now what is the reward for the player as they move closer to controlling the middle of the board? There should be a reward based on their action. So state and reward are linked together, okay? Moving from one state to the other is choosing the correct action, right, in a particular given state. All right, so that's what it is. So we're linking the state with rewards and actions. Okay, that's what it's going to be. So the reinforcement learning algorithm is really, I don't know if you want to call it, shaped by the problem how to find the optimal choice of actions for each state such that we obtain the greatest rewards over the long run. Okay, so it's not a short-term strategy. Okay, we've seen short-term strategies this semester already. Okay, and here's an example of a graphical representation of reinforcement learning environment. So we have state 1, right, and we have the reward for state 1. And we have action 1. I know it's kind of hard to see this graphic, but we have action 1. It's going to take us from state 1 to state 2. Okay? Where in state 2, we have a reward for that particular state, to reach that state, whatever that is. Okay? And this could be, remember, think about what states are when we talked about state machines. States could be things like what your level of health is, right? Where your position is in the game world. What the positions of other players are in the game world, how much resources there are left, and so on, and so on, and so on. Every possibility. The more you bake into the state of the world, the more you can be rewarded or punished based on the types of actions you take. Right? And this is, I'm talking when I say you, the autonomous character. Right? So you can see that there's a path between this state 1, as an example, and state 2. And from state 1 to state 3, but you can also see that there's different rewards depending on the different states. If we were only interested in immediate rewards, and this is an example of pathfinding. Okay, think about pathfinding, right? We're only thinking about short-term rewards with pathfinding, all right? We do this greedy first search that we talked about kind of before with pathfinding. This is something that you did in the first half of semester, right? So if we're in state 1, we have a reward that's equal to 0 in state 1. We have 2 actions possible, right? And if we used pathfinding and we said, okay, here's action 1. Action 1 is going to give us a reward of 10 to get into that next state. Or action 2 is going to give us a reward of 1. Because we're using this short-term vision or a very narrow vision, we want short-term or immediate rewards. If we were going to use this system, then guess what? The AI would always choose to go to state 2, not go to state 4, okay, with action 2. Why? The reward is greater with this set of actions, the first set. However, remember, these arrows, it's kind of like a directed graph, right? So you can either go here or here, and then you're going to be stuck with one of these 2 actions, okay? Think about this kind of scenario, right? So if I go with the short-term reward, I'm going to be going here. Okay, what's the next step? Well, the only place I can go from here is, I'm going to go to this next state, and this next state, I'm going to lose 10 points. So I gained 10 points of reward. I've lost 10 points of reward because that's my only available action to me. And then the next state is going to go back, and I'm going to go back over here where I'm going to gain 10 points. And so I'm going to waffle between gaining and losing 10 points. More or less, this is a zero-sum game. I'm not going to make any advancements here at all. Even though, from the initial state, this seemed to be a good action, overall, the reward is 0. Okay? So 0, it got plus 10, and then minus 10, and it's going to keep on doing that in a cycle. Whereas if I went to this reward, which is not normally something that happens with a greedy first search, right? Then if I go to take the next action, I'll go to the next state, which will give me 100 points, right? And then I'll get another, another 1, and then I'll get another 100, and then I get another 1, and then I get another 100, then I'll get another 1, and I'll keep doing this, and this will continue to improve my reward by doing these same actions over and over again. So if I could look ahead, several moves ahead, and take all the different possible paths, right? And again, I'm thinking more of a Dijkstra's algorithm here, as opposed to a greedy first search like A-star algorithm, right? Then we might have a long-term solution, a long-term reward compared to a short-term reward. This is your short-term reward over here. Okay, so we can think about this part here as your short-term reward, and this part here as a longer-term reward. Okay, this is where we want to go. Okay, because here typically greedy first search only thinks about the next node or the next node, whereas here we look at the entire kind of path, the entire sequence of actions, action 2, followed by action 5, followed by action 6, followed by action 5 to get the highest reward. Okay, so hopefully that clarifies a little bit when it comes to actions and rewards. All right. So again, we talked about this. Reinforcement learning is an unsupervised learning technique, is what it is. We acquire knowledge or experience independently. There is no explicit instructor to train the system necessarily, and it's designed both to explore and exploit. So those 2 things, explore and exploit its environment. Again, one thing it can do is it can handle unpredictable situations to some degree, right? However, I just wanted to point this out, that reinforcement learning is not perfect, right? In fact, if it becomes perfect, it can suffer the same negative effects of overfitting that we talked about earlier. So we're going to do a little bit of math, just a little bit, all right? So we model the environment as a network of states, like we talked about. The reward is obtained for entering a state, and what we do is the assignment of rewards may be deterministic, right, or stochastic. Stochastic meaning random, right? And so the way it would work is, if it's deterministic, then a reward would be mapped directly to the state that you're in, and that would produce a value. I like to think about this as the greatest utility again, right? The higher the utility is, it would be mapped against, from a reward state perspective. So here's the reward function, and you're just passing in the particular state to that function. That's what these brackets mean, right? And think about as a one-to-one mapping with a value. Deterministic. Stochastic is more like the sum of all actions with a particular probability, right? The probability of that action, right? So sum of all actions, right? And then we want to map that state to the reward based on that random action, where the values are mapped to the states, and the total possibilities kind of wrap up to 1. So example, if I had 5 different possible actions with different probability for doing each of those actions, let's say, the total probability would add up to 100%. So for example, if I had a 20% chance to do one action, and a 30% chance to do another action, and a 10% chance to do another action, all of those percentages would add up to 1, or 100%. Transition from state ST as an example, so to state ST plus 1, so example, the current state to the next state, is by taking some kind of action at a particular time. Okay, that's how it works. Okay, so and this is determined by some kind of probability distribution that you want to use. So you want to say, given that we have a state T, and we have some kind of action possibilities T, so some kind of actions we can take from that particular state, given that, what is the next action? That's what this means. What is the next action? So current state plus 1. What is the next possible action based on what is the probability to go to this next action based on the current state and the actions that are available? That's what this little math symbol means. Okay, the probability, or the possibility, if you will. Again, the overall goal for reinforcement learning is to optimize rewards, okay, as we navigate through the system. Okay, when we say optimize in reinforcement learning, it means certain things, right? Again, finding the largest long-term rewards, all right, obtained for entering different states, not short-term rewards. So in other words, again, think about me exploring the entire world and learning about the right sequence of actions to take, all right? So we need a policy function, and that's what it's called, a policy function, which we use to map states to actions, okay, some kind of policy function. And the policy function, we usually use a pi. I'm sorry about that, but that's what we use when it comes to reinforcement learning. And we map the state, the particular state, to the policy function, and it returns an action, all right, the right action. So think about the policy, what that policy matrix is, if you will. We'll talk about policy in a bit. So that's deterministic, okay? If it's non-deterministic, if it's stochastic, which is the way what we call non-deterministic, we have a policy function, and we pass both the state, the current state, and the possible actions, and what we get is a probability for that particular action to come out based on given a particular state. That's a different outcome than always the same action based on the state you get in. Okay, is that clear? I know that we've been talking about states and actions and different things, but does this make sense to you? So think about this from a deterministic versus non-deterministic perspective, right? We have some kind of policy function. You pass in a state in a deterministic world, and you're going to get out an action every single time. The same action, by the way, right? Whereas in a stochastic world, a non-deterministic world, you have a policy matrix, if you will, and you're going to pass in both the state and actions, right? Into that particular, into the policy matrix, policy function, right? And then you're going to have some kind of probability that you're going to get given, it's going to return some kind of action based on the state. Given the state, what's the probability that we're going to make that set of actions based on the current state? Okay, and that's what it's going to return. Almost like a set of actions. So one of the things we need to do, and this is something we talked about last week in some ways, this idea of a policy value estimation. We kind of did this, a DSE is what we called it, right? Instead of a PVE, policy value estimate, right? So how good is the policy? So for example, if I'm making a policy function, where is this policy function coming from? This policy matrix, if you will, right? Well, in the beginning, we have a very poor policy matrix because remember, we're not making one we're not giving any instructions to the, to the AI in this case. Where if we're using reinforcement learning, what we want is for the AI to learn about the environment on its own as much as possible, right? And so we don't give a very good policy matrix. The policy matrix is evolved over time. Okay, so it creates this policy value estimation. And what we want to do is we want to give it a very generic policy value estimate at the beginning, so to give it some kind of guidance to get going, and then afterwards it develops its own behavior. So a good policy picks actions that move us into states with good long-term rewards. Looking at this previous thing, it's going to move us into this thing. It's going to go from state 1. It's going to take action to. It's going to evaluate over the long term that, you know what, taking this action, immediate rewards is going to be low, but long-term rewards is going to be high. That's what we want it to do, and it's going to need to evaluate future potential paths. And I want you to think about this as all the possibilities, all the future possibilities, to some degree. Okay, remember, we can't look at every possibility, even in chess, because there are many different kinds of sequence combinations in order for you to have a winning strategy, right? And another even more complex game that we want, if let's say we're going to try and map or predict, is something like the game of Go, where it's many more possibilities than chess in some ways. So we have to give a limit, to kind of understand what a good long-term reward is, and how deep we're going to go. How many moves ahead are we going to look before we stop? Okay. Otherwise, it'll be inefficient. So long-term rewards is a reward for being in the current state and all future rewards possible to obtain from that particular state. Okay, so example would be, if I'm looking at reward T, we want to use the current reward that we're getting, and then we have something called a discount function. That's what this gamma is, right? The discount function for all possible future rewards. So for example, but from this particular state. Okay, I know this is kind of, math. Don't worry. I'm not going to ask you these crazy questions on a test next week. It's just from an understanding perspective. So think about this as the discount term, right? And the discount term goes between 0 and 1. So it's not going to be perfect, okay, every single time. But think about from this particular point in time and this particular reward, from this point, there's a sequence of rewards that I can get based on the possible actions that I have available to me. Think about this as we don't want a single instance or trajectory of rewards. What we want is a long-term value for choosing a state. In other words, future rewards that are possible based on all the possible options that we have. Now that would be in an optimized state, an optimal state, if we can get all the possible actions. Remember that we don't have perfect knowledge, right? And we're never going to probably have an AI until we get to quantum computers, as an example, and that would be very scary, that can think an infinite amount of moves ahead. We have, a finite number of possibilities based on the ability of our machine. Okay, not just hardware, but our algorithm as well. Time is also a factor. So imagine if you're waiting for the AI to make a move. It's analyzing every possible sequence of moves from your current state in the world. The game would probably slow down to a crawl, if not stop altogether, until the AI is ready to make its move. Or the AI would just sit there asynchronously in its own thread, and then while you're doing your thing, it would just freeze. Well, it's trying to calculate what your next move is, but meanwhile, in real time, you're making your move, right? So it can't look at every possibility. It'd be optimal to do so. But remember, what it's doing is it's learning, it's kind of long-term rewards. So again, when we want to do a policy value estimate, this is what we're setting up here. We want to look at all future potential rewards. So long-term rewards for all the next states, SJ, from the current state, SI, right? So again, we want to pass it into this, the value that we're going to get, right, for the next state and the next state and the next state. So all possible long-term rewards. So for each state, Sj, and basically want to weight it by the probability that you're going to get to the next state given the current state. So here's the current state, given this little line here means given the current state that we're in right now, what is the probability that you're going to get to the next state given where we are right now? Okay. And then what you want to get is, again, we're just building up the policy value estimation function, all right? We're basically saying that the value of all possible future states is equal to the reward of the current state plus all future possible rewards. Okay, that's how it works. And this kind of expands to this formula here. I'm not going to go too much more into the math, which expands to this formula here. And what this formula is a recursive formula that we use, and we can rewritten into a vector equation that looks like this. The vector, the value vector, all right? And again, vector meaning that the direction to get the best value is equal to the reward vector plus some kind of discount function times the probability of getting all future possible values from that particular state. Okay, that's how it works. And so what you have is P is a conditional probability transition matrix with rows being the current state and columns being the next state. Okay, so you kind of create this probability matrix. I'm hoping you guys are kind of with me on this one. So again, we can obtain the R vector, the reward vector, from traversing the world. So we go through the entire world, and we look at each of the states from state I to state J, all possible states, and we add things in, like the position of the state in the vector, the reward vector, and then we get the reward value obtained from the reward vector, all right? And then P, the probability matrix, as an example, can also be built from a trajectory or traversal by starting with some kind of n by n array, where n is the number of states, and we start this off with all zeros. We start off the probability matrix as 0. We don't have anything. And what we're going to do is, as we traverse the world and we get a reward, we increment the probability or the think about the reward matrix, if you will, as we move through the world. So every time I do a positive thing, almost like I'm tallying all the positive choices for that particular state. Okay. So if I move from state 1 to state 2, let's say, and then again, we're thinking about states. Don't just think about a position. Think about all possible things we want to track. Position. We want to track things like health. We want to track things like ammo. We want to track things like, again, these are all different things you can track, and things that are internal to the character as well as external to the character. The more things you track in each quote-unquote state, then the more accurate your probability matrix, but also the more complex and the more difficult for you to traverse. All right, so we have to kind of create a balance of how many things you want to track in each particular state. Okay. Once we look at rearranging the equation, then what we can get is, again, we get the probability matrix, and then we get the inverse. The inverse matrix. As an example, we kind of apply the inverse as a rule, and then what we get is, once we multiply the matrices and the inverse together, we get this kind of equation. I'm not going to move too much into that. And this equation is solvable when we follow a specific policy. So again, this idea of a stochastic policy function where we pass in a state and an action, and we get out, given a particular state, what are the probabilities to get a particular action. And that's overall how it works from a mathy perspective. All right, so here's the general approach. We have a policy function. We have a way of evaluating a policy with a policy value estimate based on how good the policy is, right? We want a best or optimal policy that gives best long-term rewards. And we use the star, P star, right? So this is the optimal policy, right? How do we find it? Policy iteration. And what that means is we take the existing policy matrix. And again, this is almost like a a grid, if you will, or a matrix, right, of values that start off at 0, so no rewards, or -1. It really depends on how you want to start it off. And then what you do is you tally up rewards doing certain, as you map certain states to actions, right? And that's how you create your policy matrix. And the policy matrix is going to be applied according to the kind of actions we take, okay? So it's going to learn through the policy matrix what the best sequence of actions to take are from the current particular state, okay? So steps to do it. First, arbitrarily choose a policy. Again, you could, and the way to arbitrarily choose a policy is kind of a little bit weak supervision. So it's your knowledge of the world. Let's say if you're designing a particular level, or you can give some basic rules for the AI to initially follow. That's what the arbitrary policy matrix is, okay? And then what you want to do is you want to perform this policy value estimate, all right? And you're going to follow the policy for a large number of steps, right? And then what you want to do is you want to perform policy improvement. Okay, how did I do it? How many rewards did I get? You might have a reward matrix. So I have a policy matrix. Here's what I did. And here's my reward matrix based on what I did with the policy. So I've been given a policy to follow, almost like a behavior policy, right? And then I have this reward matrix, right? I'm going to map my rewards to the policy and say, does this policy make sense? That's what the AI is going to do, right? And if the policy gave me a set of sequence of actions that did not give me good results, I'm going to improve the policy by saying, don't do those actions, okay? Only do these sequence of actions given this set of states. And then what we're going to do is we're going to keep on iterating. We're going to keep on iterating to improve the policy over and over again. Now this could require several thousand iterations through the game world, all right? So again, a lot of times what we do when we use reinforcement learning is we do it offline, okay? We don't do real-time or online learning with this because it takes so long for us to do this, right? So what happens is it's proven over time to converge to some kind of thing called the optimal policy, all right? Where, and again, there's something called a Markov property that we talk about in AI, which is the future state of probabilities that are dependent only on the current state. Example, this is also something called a memory-less property, okay? And one of the things is we have to also ask our questions is how long is long enough for accurate estimation? Again, we want to iterate a bunch of times through the game world in order for us to improve our policy, right? The better our policy is, the better the rewards we're going to get for a mapped set of actions. Here's our action, here's our possible rewards, probability of rewards, right? Based on our policy matrix, right? How long can we estimate? And sometimes what we want to do is also, give a value to, as an example, future possible states. And we can do this with the idea of goals. Remember goal-oriented behavior from last week? We can apply the goal of each AI to a set of states. And this is where we can get positive rewards. All right, so things that we need to do to set this up. We need to set rewards for every state. We need to also determine a discount value y, or a gamma actually is what it is. Choose an initial policy function. Choose how long to run the exploration trajectories, right? And choose how many exploration trajectories to try before policy improvement iteration stops, okay? If we don't explore long enough, you will get poor value estimates and it'll take longer to converge to the optimal policy. If you explore too long, as an example, we're not going to have much play, right? It's going to take a long time for you to get something that's realistic, okay? So you need to kind of find the right, the right length, the right iteration times to get this, again, part of the best possible policy, the optimal policy. Okay, getting through it, guys. So what we want to do is, when we want to build this probability matrix, again, there's we talked about a bunch of things, a bunch of different matrices. One of them is this, policy matrix. Then we have the reward matrix. And then we have a probability matrix. All right. We start with this zero matrix. A zero matrix means zeros everywhere. And then, like we said, during exploration, what we want is for every transition from state I to state J, so from the current state to all possible future states, we want to increment the probability of us getting to that next state by 1. And that's how we create this probability matrix, or policy matrix, if you will, right? At the end of each exploration, we calculate the sum of all probabilities going from state I to state J. That's what we want to do. And we divide each by the total number of iterations, and this will convert your matrix into a probability matrix. All right, so that's kind of the way we do it. The chances that you'll get to that next state from the current state based on the rewards. Okay. Okay, so that is classic reinforcement learning, but we need a simpler solution because this is like really, challenging to code. Imagine if we're coding something like that, right? And by the way, we did it. Okay, it's not like we haven't done it before. Both at the university level and the college level. But there's something called Q-learning that treats the game world as a state machine. And this can kind of help us. This is another approach to doing reinforcement learning. So think about this. At any point in time, the algorithm is in some state. We talked about this already, kind of, right? State should encode all the relevant details about the character's environment and internal data. Again, we talked about this as well. Health, ammo, position, other player's position, advantage, disadvantage where they are physically, from a behavior perspective. Maybe they've got resources they got to think about, whatever, right? As much in the algorithm that you can fit in as possible that's realistic. The more you fit in, again, as an example, then the more complex your state is going to be, okay? But the state can have many dimensions, if you will, right? If the health of the character is significant to learning, if the character finds itself in 2 identical situations with 2 different health levels, then it will consider them to be different states. Okay, so I could be in, example, the exact same position, right? Let's say from an XY coordinate perspective, I could be at coordinate space, 30, 100. But I could have different health levels, different resource levels, different positions for other players. That particular place, even though I'm in the same position, is considered a different state than if I was in the other state, which is I had, let's say, 100 health instead of, let's say, 50 health. If I had more resources or less resources. Each change to my to encoding my state details creates a different state. All right. Anything that I don't include in the state can't be learned. So if I don't include things like health, then I'm not going to consider health. It's not going to be considered when it comes to my learning. If I don't care about health. So what we want to do is we want to encode all the pertinent information for that particular AI. Not everything, right? We want to encode only the goal-oriented information. The things that are going to make it, have the highest utility, if you will, for that particular, AI, okay? And that's what we want to encode in the states. We talked about this. Q-learning doesn't need to understand the components of a state. As far as the algorithm is concerned, it's just integer values, a state number. So, for example, a state number could be things like, say, so state 0 would mean something like I have a health of 100, I have my ammo is 100, and I'm in a position that's 0, 0. Okay, that could be state 0. I'm just giving an example. The game, on the other hand, needs to be able to translate the current state of the game into a single state number for the learning algorithm to use. And typically we don't have to go the other way. Okay? So one thing about Q-learning is it's a model-free algorithm, all right? Because it doesn't try to build a model for how the world works, okay? So it's the other way we talked about earlier was a model. It was a kind of a structured algorithm where we want to try and explore the world, as an example, many times ahead of time, in order for us to create a probability matrix where we map rewards to actions. Okay, this is not that. Not exactly. It just simply treats everything as states, right? So where algorithms that are not model-free try to reconstruct what is happening in the game from the states that it visits, model-free algorithms such as Q-learning, it tends to be easier to implement because we only care about the states that it knows in its Q matrix. Okay. And in many games, all actions are available at all times. All right, that's also something that we can do. For more complex environments, however, some actions may only be available from when the character is in a particular place, right? When they have a particular object, or when other actions have been properly carried out, a sequence of actions from before. Okay. So after the character carries out that action in the current state, the reinforcement function should give it feedback. Again, going back to what we said, it's all reinforcement learning. So is it positive or negative feedback, right? Usually positive, and negative, usually we give 0, all right? Although there's no limits on the values that we can apply to the function, typically what we use is a range of -1 to 1. And again, you guys are going to see numbers like this in AI or even in video games in general. We're going to see numbers between 0 and 1, right? Normalized. We're also going to see numbers between -1 and 1, also normalized, but giving us a broader range of values, right? Where -1 could be really bad, right? Like terrible, this is a very bad action and a degree of bad actions, as opposed to here's some really good actions from 0 to 1, okay? Again, there's no requirement for the reinforcement value to be the same every time an action is carried out in a particular state. There could be other contextual information not used to create the algorithm state. And as we saw earlier, the algorithm can't learn to take advantage of the context if it isn't part of its state. In other words, if I don't have health as part of its state, I can't learn, as an example, that particular thing is a good thing to do for health if we're not tracking health. Whatever we're tracking or encoding is the thing that's going to help us improve our algorithm. But one thing it'll do is it'll tolerate its effects and learn about the overall success of an action rather than its successes on just one attempt. Okay? After carrying out this action, the character is likely to enter a new state, right? And carrying out the same action in exactly the same state doesn't always lead to the same state of the game because of other characters that are in the game. Okay, so what the good thing about Q-learning is it's almost like not just unsupervised, but also model-free. So I don't have to necessarily do a lot of previous runs. I can do some offline learning, but some of the things that I'm going to do is going to be in real time. Okay. Here's an example. A character in FPS is trying to find a health pack and avoid getting into a fight. The character is ducking behind a pillar. Wow, we've been doing this for assignment 4, right? Not quite an FPS. On the other side of the room, an enemy character is standing in the doorway looking around. So the current state of the character may correspond to in room 1, hidden, enemy near death. Make sense? That is the state of the character. It may choose the hide action, or maybe it chose the hide action to continue ducking. Okay? So let's suppose the enemy stays put, so the hide action leads back to the same state, so it chooses the same action again and again. This time the enemy leaves, so the hide action now leads to another state corresponding to in room 1, hidden, no enemy, near death. Okay, so that's a different state than the other state, which was in room 1, hidden, enemy near death, right? No enemy near death is different than enemy near death, so there's two different states. Okay. Powerful feature of Q-learning algorithm and most other reinforcement algorithms is that it can cope with uncertainty, right? Again, there's 4 elements that Q-learning looks at. The start state, the action taken, the reinforcement value, and the resulting state. And I know this is a terrible thing, especially now during our pandemic, but it's SARS, right? Which is the way it's been laid out. The SARS, it's an experience tuple or tuple, depending on how you want to pronounce that, where you have the initial state, all right, and then the final state, if you will, or the resulting state. So it goes through this, this sequence, right? So initial state, some kind of action, some kind of reinforcement value, and then the final state based on that sequence. Okay. One thing that Q-learning is named for is this idea of quality of information, or Q values. It holds that about each possible state in action. And the algorithm keeps a value for every state, an action has tried. Very similar to what we talked about before with the policy matrix, right? So the Q value represents how good it thinks that action is to take when it's in that state. So for example, I'm in a particular place. I'm in room 1. I've got, low health. There's no enemy near. What's my next step? What do I do based on that particular state? I need to take these possible actions based on what the quality information that it has in its Q matrix, which we're going to talk about in a second. So the experience tuple or tuple is split into 2 sections. The first 2 elements, state and action, are used to look up a Q value in the store. And when I say the store, think about this as the Q matrix. All right. The second 2 element, reinforcement in the new state, are used to update the Q value based on how good the action was and how good it will be in the next state. Okay. So again, it's very similar when we look at the algorithm. Is again, we have the quality function. We pass in state and possible actions, and what we want to do is we want to say that take 1 minus the learning rate. Okay, that's what it is, and usually the learning rate is like how good I'm going to learn based on what's positive to do and what's negative to do. Right? If I made this 1 every single time, then basically what you're doing is you're removing this non-deterministic possibility. If the learning rate you shouldn't make the learning rate 1. It should be something much lower than 1. Usually it's something like 0.1. Plus, as an example, this other part here, where alpha is the learning rate and gamma is the discount rate. Both are parameters of the algorithm, and the rule is sometimes written in slightly different form with the 1 minus the alpha multiplied out. Usually we take it out altogether. But basically what the Q-learning rule blends the 2 components using the learning rate parameter to control the linear blend. So depending on, and again, the linear blend is between 0 and 1, where 0, you don't want to use quite 0. You want to use something in the middle between 0 and 1. And you need to play with these values in order for you to get the right amount. And usually what they say is, when we look at if I look at the first component, which is the Q value, that's what we call it for the state in action, we keep part of the current value in this way. What it does is we throw away the previous information that was discovered. Okay, and the second component, right, what it does is it uses these 2 elements, right, where R is the reinforcement value, right, from the experience tuple. And what happens is we have this particular equation. I'm not going to go into too much, but more or less, here in the next few slides, it talks about how to generate the how to set up each of the elements or the components of the experience tuple, if you will, or tuple, and what the right values are, for each of these things to start with. So example, discount rate should be in the range of 0 to 1. A value greater than 1 can lead to overgrowing Q values or overfitting, like we talked about. So they want to try and keep this value low. And it talks about how to set up this experience tuple. Okay, so far we've covered reinforcement function, the learning rule, and the internal structure of the algorithm at a very high level. I'm not going to go into the math too much. We know how to update the learning from experience tuples and how to generate these experience tuples from states and actions. Again, it's all mapping states and actions. And usually what you do is reinforcement learning systems also require some kind of exploration strategy, like we talked about earlier, or a policy for selecting which actions to take in any given state. And this is obviously, a lot of times it's called the policy matrix or just the policy. Okay, so very similar to what we talked about earlier, right? One thing to note is that basic Q learning exploration strategy is partially random. Why? Because we don't want to take the same sets of actions every single time, right? So make it less deterministic, more stochastic, right? And the reason why we want to also take random actions is because then we don't have to do as many iterations, right? We want to randomly, kind of explore the world instead of exploring the world systematically. Again, my thoughts are thinking about things like Dijkstra's algorithm that kind of does pathfinding for the entire all the paths that it looks at, as opposed to A star. So in my mind, Q learning is kind of like an A star algorithm for reinforcement learning. That's kind of what it is. Again, the degree of randomness can be controlled. Okay, so how much random do you want in your algorithm? If the and again, a convergence. If we want to converge to the optimal policy, if the problem always stays the same, the rewards are consistent. Usually they're not. If we're in a random kind of game environment, further running of the learning algorithm will not change any of the Q values. And when this happens, we've kind of converged to the optimal value. So sometimes what happens is in Q learning, we start acting under the influence of our Q matrix before learning is complete. And a lot of times what happens is, and this happens because we want to optimize our learning. We want to make it so that we can learn quicker, is what this Q matrix allows us to do. And here's an example of the general Q learning system with a structure. All right, so this is some pseudocode that is provided by the book when it comes to Q learning in general. All right, I'm not going to go through it, but more or less, this maps the idea of a Q matrix or a quality matrix, and allows you to increment, the quality matrix based on rewards. Okay, so I'm not going to go too much more into this algorithm, but just to add as a summary, right, as an example, right, the summary is that I'm not going to go into too much of this. This is just talking about how you prune the learning rate, how you set it up, and so on, because each of these values are part of the this is almost like an appendix where I'm talking about the gamma here, which is the discount rate and how to set that up. And usually they recommend certain values, like 0.75 is a good initial value to try with the discount rate, as an example, to create your Q matrix. And rho, from randomness for exploration, again, a good value to learn is something like 0.2 for the rho value. Nu, the length of the walk, how many iterations that I'm going to do. Again, it's in a range of 0 to 1, and usually a value of 0 would mean that the algorithm always uses the state in reach in the previous iteration, and the closer you get to 1, then it's going to do different longer states. And again, they recommend something like a value around 0.1, which is normally suitable for the length of the walk. Okay? And really that's it from a high level. So, I mean, again, I know that there's some highfalutin math here, but let me sum up to say this, all right? Reinforcement learning can be something that is awesome for us to use. If you actually look online, there's a ton of algorithms that can again, you want to map the idea of mapping, kind of your current state to a set of actions. Okay, so if I was going to talk about reinforcement learning, so think about this, right? I have my current state. What is my current state? Can we track this, right, as an example? And what are the next possible actions that I can take? Okay, cool. Now, which of those actions are going to give me the highest reward in the long term, right? And now there's a bunch of different techniques to get there. You can use classic reinforcement learning, which is more unsupervised, or you can use something like Q learning, which does things more randomly, stochastically. So it just randomly chooses stuff and creates this idea of a Q matrix, right? It really depends on how you want to go. But what you're doing at the end is you're creating a policy, a behavior policy, more or less. And then what you're doing is you're going to map your behavior policy. You're going to improve your policy or through policy iteration to be better and better at the actions you're taking. And when I say you, again, I'm thinking about the autonomous character. You're going to improve the policy matrix, right, through policy iteration. Okay. So, and what you want to do, the way you improve that is through a series of rewards or punishment, right? And it's kind of how we learn in real life. If you think about a baby, baby's going to feel happy or not happy based on what they get. If they get food, they feel happy. If they don't have food, they're unhappy. And so that's how babies cry in real life, right? So it's kind of the same for this. Think about your autonomous character as a baby. You're going to reward it or not, and if it's not rewarded, it's going to be crying. I'm sorry to say it that way, but that's really what it's like, and it wants to be rewarded as much as possible, right? So it's going to continue to try and find the best paths, the best sequence of steps from its current state to all future states, based on its knowledge, right? So it can make the best possible action. Okay. Again, this is beyond just regular decision matrices, beyond basic decision trees or behavior trees. This is creating a way of remembering from game to game what the best choices are based on the current state. Okay, any questions? This is I know it's kind of highfalutin, but we have to talk about this stuff because if you're interested in game AI, this could be very well the next frontier for you. And hopefully you are. Hopefully this inspires you or makes you think about how to create your own algorithms, your own techniques for learning. Again, it can be very simple. It doesn't have to be as complex as a Q-learning algorithm. It doesn't have to be as complex as the standard reinforcement learning algorithm. But you want to be able to map some kind of rewards to actions, right? And depending on the number of rewards that you get, right, you want to take a particular set of actions to make the AI more realistic, so it behaves more like a human, more like a genetic algorithm, as opposed to it's always going to do the same things. It's something that you can predict, right? But in reality, making such an algorithm takes time, and it takes sensitivity and the experience of the AI designer to kind of think about how we're going to map rewards to actions. Okay. Will we have code examples? Yes, there are code examples in the PowerPoint. Will we do it in real life? No. It's going to take us. This would take us several weeks of designing for us to get it done. We'd have to make a policy matrix if we're going to do the reward, the standard reinforcement learning thing, or a Q matrix. But there's some great. I'm going to give you some great resources. I'll link them into the. And when we come to the lab piece, I'll put them up on Blackboard. There's some really great resources online to help you with developing, kind of using Q learning. I think Q learning is the right approach for us if we're going to do anything, any kind of reinforcement learning, because I think it's easier to map than our classic reinforcement learning algorithm. Nope, not that I know of. This is probably your only AI course that I can think of, that I know of at George Brown. But I think the great thing about this is that Maxim, what it's trying to do is push you into a direction, right? Where what's the next steps for you after college? Where do you go from here? Remember that just because you are part of the game programming program here at George Brown, it doesn't mean that you're going to be necessarily a programmer, for gameplay or for tools or for whatever. It could be. There's so many aspects of game development that you can end up anywhere. And hopefully, something like this kind of talk, or the idea of reinforcement learning in games, can inspire you to move to something else like AI, where we need more people in that in that sphere, in that dimension. All right, so what are we going to do for our lab? What I want to think about in lab again is more stuff for assignment 4. I want to work with you guys on assignment 4 so that way we can get it done. I also want to see where you're at. So when we get together today, there's not going to be a lab exercise. I really want to kind of discuss with you guys where you're at with assignment 4. I want you to show me where you're at, and this way I can help you. It's more of that kind of thing as opposed to me telling you what to do and giving you some examples. However, I will talk about what I recommend, which is a state machine. I think a state machine is probably the easiest thing to do compared to a decision tree. Well, actually, it's either a decision tree or a state machine. A behavior tree, I think, is more complex to code. It gives you more realistic behaviors, but for our example, I think, or our situation, either a state machine or a decision tree would be probably best. Okay, and we're going to talk about those two possibilities in lab. So I will see you guys in lab. The first lab starts at 12, so that's in about 25 minutes. All right, and then the next lab starts at 3 to 5. Again, I will try and record our lab from 3 to 5 and give you guys a chance to practice some of the coding that we're doing. Okay. Will the exam be during the lecture? No. As I mentioned earlier today, thank you for asking that question. The exam I'm going to, which is the final test, is I'm going to release either Monday or Tuesday, and you'll have all week to do it. All right. It'll probably be something like 45 questions. You'll have a limited amount of time, probably 45 minutes to do each test. Well, you'll have several attempts that you can make to improve your score. Thanks, Paul. See you later. So that is the exam. That's how we're going to do the final test. And the final test is going to be released again Monday or Tuesday next week, and you'll have until Friday to get it done. One thing to note is that there will be no extensions. Yes, it'll be only based on the second part. So it's not going to be all-inclusive. Again, Maxim, thank you for asking that question. So it's not going to be like the entire course. I think that's unrealistic, for us to make it the entire course. So it's going to be modular, so only the second half of the semester it'll cover. The first half you've already covered with Alex. You'll only have 2 attempts, yes. Again, unless you're in some kind of extraneous circumstance, or something like that where you make a mistake or a technical issue, you let me know and I can reset you. Okay? Anyone else have any questions around next week? So again, recap. Next week, there's no standard lecture next Friday. Next Friday, we're going to get together to discuss any issues. It's going to be like an open office hours. Then I'm going to be available for you guys to help you with any kind of questions, marking of any of your stuff, as well as any questions related to your assignment 4. If you have any technical questions, it'll be kind of an open day where I kind of open up the Zoom call from 10 o'clock in the morning until about 5 o'clock in the afternoon. I'll have an open call, and then it'll be one break. Again, I'll take a break between, let's say, 2 and 3 in the afternoon, just like normal. And then I'll resume from 3 to 5, but it'll be basically open office hours and open help for anybody who needs help with their assignments or anything else. Okay? Guys, otherwise, thank you so much. I'll see people in the first lab at 12 o'clock where we're going to be talking about different approaches now to solving the problem, which is assignment 4. Okay? Thank you so much. I'm going to stop recording now, and we'll see you during our labs.